Hi, welcome back. In this section, we're going to look at section 5.1, which is all about hydrolysis of salts. And so some of the goals for this is to define what hydrolysis is and explain how we know whether a salt will be acidic, basic, or neutral when placed in water. Finally, we're going to look at how to calculate the pH of a salt solution, which is going to take us back to our ice tables. So with hydrolysis, what we're actually doing is to look at the word hydrolysis means to split apart using water. So it's a reaction of an ion with water to produce either the conjugate base of the ion and hydronium or the conjugate acid of the ion and hydroxide. What we're basically doing with this is taking our salt, splitting it apart, removing any spectator ions, and we'll talk about that in a second, and then trying to figure out if the remaining cation or anion acts as an acid or a base. And hydrolysis explains why some salts act as acids in water while others act as bases. So here's a couple of examples. Sodium acetate, for example, acts as a base in water, whereas ammonium chloride acts as an acid in water. This really explains why. So once salt is put in water, it splits into cations and anions. And those cations and anions may undergo base hydrolysis, acid hydrolysis, or they may both be spectator ions and the solution is neutral. Spectator ions, we've seen spectators before, and those are ions that do not participate in a reaction. So they're unable to undergo hydrolysis. Any spectator ions that we have relate to the strong acids and bases. So if you'll recall, with a strong acid, we have a one-way reaction taking place. So when a strong acid breaks apart, it breaks into its conjugate base and it breaks into a hydronium ion. And that conjugate base never actually gets to act as a base because it's a one-way reaction. So all of the anions of strong monoprotic acids, including ClO4- and our iodide ion and bromine ion, chloride ion, nitrate ion, all of those anions of the strong monoprotic acids are spectator ions, so they are not able to undergo hydrolysis. Cations of strong bases as well, and that includes all of the alkali metals and alkaline earth metals, because when we combine those with hydroxide, like lithium hydroxide, they only form that one-way reaction as well. None of these get to act as an acid as well. So all of those are spectator ions as well. And just so you're aware, you don't have to memorize that list. Besides the alkali and earth metals and alkali ions. The bases here, if you take a look at the bases of those strong acids, their conjugate bases are all spectator ions, with the one exception of the HSO4 at the bottom, because that undergoes another ionization as well. So here's a quick check. It says circle the ions in the following list that represent cations of strong bases. Circle the ions in the following list that represent the conjugate bases of strong acids, and circle the following salt whose ions do not hydrolyze when dissociated with water. So take a minute to see if you can go through those, pause the video, and then come back for the answers. Okay, so here's answers to those solutions. You can see in the first question here, we're looking at all of the alkali metals, that's the rubidium, cesium, and the alkaline earth metals, calcium and barium. In the second one here, the ions that represent conjugate bases of strong acids, those are all found on the right-hand side of the table of those strong acids. So we've got the perchlorate ion, the chloride ion, and the nitrate ion. And then down at the bottom, circle the following salts whose ions do not hydrolyze. We're looking at the ones that have both of them being spectator ions. So there's the rubidium perchlorate, the barium iodide, and the calcium bromide. So here's a chart that kind of goes through how we know something is going to be acidic or basic. So we can have neutral salts, and that's when we have a cation where we've got the cation of a strong base and an anion of a strong monoprotic acid. So if both things are spectator ions like sodium chloride, we're going to get a neutral salt. So when we put sodium chloride in water, for example, it's going to be neutral, pH of 7 at 25 degrees Celsius. On the other hand, we could have a basic salt. So if I put calcium carbonate in water, for example, the calcium is a spectator ion. It's the cation of a strong base. However, that carbonate ion will go on to hydrolyze. So the carbonate will mix with water and form a hydrogen carbonate ion and hydroxide. So it will be basic. Acidic salts are when we have a conjugate acid of a weak base and the conjugate base of a strong acid. So we've got a spectator anion. So with this one here, we've got C5H5NHNO3. When it splits apart, the NO3 is going to be a spectator ion, and that H5 or C5H5NH plus will go on to react with the water to form hydronium. So it will be an acidic salt. Again, we can also have an acidic salt if we have a small, highly charged metal cation as well. So you may have taken a look at the chart and looked at the there's hexoaquo chromium and hexoaquo aluminum, for example. Those are the small, highly charged metal cations, and those will all undergo hydrolysis and form hydronium as well, so they act as acids. Another situation where we need to kind of do a little bit of math is if we have an acidic salt and a basic salt. So if we've got a conjugate acid of a weak base and a conjugate base of a weak acid, we're going to have to do a little figuring out to see which one is stronger. So here's an example here. We've got a chromium ion when we split this apart, and then we've got an acetate ion as well. So the chromium will act as an acid, but the acetate will act as a base. So we have to figure out which one is bigger. What we do then is compare the Ka and the Kb value. So I'm going to look at the Ka value of the chromium ion, the hexoaquo chromium, and then I'm also going to look at the Kb. So I'll take Kw divided by the conjugate acids Ka, and I'm going to compare that. So we'll do a few questions like that later on. The last situation is if we end up with an amphiprotic ion. So you can see here an example of an amphiprotic ion. If we have sodium hydrogen carbonate, the sodium is a spectator ion, but the hydrogen carbonate can act as an acid or a base depending on the situation, depending on the solution. With the hydrogen carbonate, what we're going to do is we're going to look at its Ka, and we're going to compare it to its own Kb. If the Ka is higher, it'll act as an acidic salt. If the Kb is higher, it'll act as a basic salt. So with this practice question here, it says, without performing any calculations, rank the following salts in order of decreasing pH of their 0.1 molar aqueous solutions. So we're looking to try and figure out what is the most basic and then go down to the least basic. So what I'm going to be doing is dissociating all of those. I'm going to take the sodium separate from the sulfite, and the sodium is a spectator ion, so I'm just going to look at that sulfite and try and figure out where it ranks on the chart. With the lithium and the fluoride, I've got lithium as a spectator ion. The fluoride, however, acts as a weak base. So I'm going to figure out where it ranks on that base chart. So we're looking at that relative strength of Bronsted-Lowry acids and bases chart, and we're using it to figure out which is the most basic down to the least basic. So when we do that, here is the solution. So the most basic is that K2CO3. The least basic is the KNO2. So we're looking at ranking those. Here's another type of question. This time we're asked to do some calculations. It says sodium carbonate is often used in the manufacture of glass, and it's a laundry additive to soften water. 200 milliliter aqueous solution of 0.5 molar sodium carbonate is diluted to 500 milliliters. Calculate the pH of the resulting solution. So we've got a few things that we have to do in this question. First off, we have to decide whether we have an acidic solution or a basic solution. And if I have sodium carbonate, if I dissociate that, then I have sodium and carbonate ions that I have to look at. The sodium ions are going to be a spectator ion. The carbonate, however, will act as a weak base. Now that weak base is going to be diluted. So there's where we're going to look at in our first step. So we're going to find the initial concentration of the carbonate. I'm going to use my dilution formula, C1V1 equals C2V2, to find that initial concentration. So I know that my final concentration of, final volume of the carbonate is 500 milliliters. I know that I'm starting with 200 milliliters, and I'm starting with a 0.5 molar solution. So what I'm doing is I'm going to calculate C2 in this particular situation. So I'll divide both sides by 500. I get a final concentration there of sodium carbonate at 0.2 moles per liter. And because this is going to split into 2 sodium ions for every 1 carbonate ion, my final concentration of carbonate is 0.2 moles per liter. And I'm crossing out the sodium there because it's a spectator ion. So there's step 1. I'm taking the negative log of, and going to be finding my POH. So finding the negative log of the 5.98 times 10 to the negative 3 gives me a POH of 2.22. The last thing that I'm going to need to do with this question is to find the pH of the resulting solution. So to find the pH, I'm going to take 14 minus 2.22, and I get a final answer of 11.78. So these questions are very, very similar to the weak base questions or the weak acid questions that you were given in chapter 4. The only difference now is having to do that hydrolysis reaction in the first place. Here's another question. It says, what concentration of NaHCOO would be required to produce an aqueous solution with a pH of 9.20? Begin by writing the equation for the predominant equilibrium present in the solution. So with this one, what I'm looking at is the sodium is going to split apart from the HCOO minus. And the sodium is a spectator ion, so I'm going to ignore it, and I'm going to focus on the HCOO minus. That HCOO minus is going to react with water to form a base and the conjugate acid. So I'm going to fill in my ice table, looking for that initial concentration of the HCOO minus. And the way I'm going to get that concentration of OH minus and HCOOH is by going through that pH. So I know that my pH is an acid land calculation. POH, I'm going to take 14 minus the 9.20, and I get a POH of 4.8. To find the hydroxide from that, I'm going to take 10 to the negative 4.8, and I'm going to be plugging that 1.58 times 10 to the negative 5 into my ice table. Now I'm going to go to my Kb formula. I know my Kb is going to be 1 times 10 to the negative 14, Kw, divided by the Ka of the conjugate acid. Okay, so I'm looking at the conjugate acid, HCOOH, and that Ka value is 1.8 times 10 to the negative 4, just taking that right off the chart. So my Kb value for HCOO minus is 5.6 times 10 to the negative 4. And Kb is equal to the products over the reactants, 1.58 times 10 to the negative 5. I'm going to square that because there's 2 of them. And then on the bottom, that initial concentration, C0, minus 1.58 times 10 to the negative 5. When I go through that and I solve for C0, I get a concentration of 4.5 moles per liter of sodium HCOO minus. Okay, so there's my initial concentration. Third question here is a sample problem. And this time I'm given a Kb for pyridine. And I'm asked to calculate the pH of a 0.1 molar solution of C5H5NHNO3. So for this particular question, I'm going to do I'm going to split apart the C5H5N and the HNO3 minus, and I'm going to take a look at which one is stronger. Now it turns out that when I compare the Ka of the HNO3 with the Kb of pyridine, the Kb is higher. So I'm going to use that as my predominant reaction. So I've got C5H5NH plus mixed with H2O, and I get C5H5N plus H2O. So with this particular one, I'm writing down all of the stuff that I know to begin with. I have a 0.10 molar solution to begin with. I'm going to assume that I'm starting with 0 of the conjugate acid and the water. And with this one, I'm adding X to the right-hand side, subtracting X from the left-hand side. And at equilibrium, I get X, X, and 0.1 minus X. So I'm going to go ahead and I'm going to plug those into my equation. My Ka equation is going to be 1 times 10 to the negative 14 divided by 4.7 times 10 to the negative 9, which were given in the question. The Ka in that situation is 2.13 times 10 to the negative 6. So when I plug that into my equation, I get 2.13 times 10 to the negative 6 is equal to x squared divided by 0.10. And I'm going to assume it's 0.10 and just get rid of that x, assuming it's very, very small. When I solve for x, I get x is equal to 4.61 times 10 to the negative 4. There's my concentration. And to find the pH of this solution, I'm going to take the negative log of that, and I get a pH of 3.33. Okay, another quick check here. So lots of kind of questions just to see if you're understanding hydrolysis. Again, nothing really new in this case. We're going to circle the salts below that will produce acidic aqueous solutions. So split them apart, cancel out any spectator ions, and then see which ones will undergo an acid hydrolysis. So there's my first set of solutions. That NH4 plus will undergo acid hydrolysis. The I is a spectator ion, so it will not participate. With the chromium chloride there, when we split those apart, the chloride is a spectator ion, but that chromium goes on to react with water and form hexoaquochromium, and that will go on and act as an acid. Same with the iron. The NO3 is a spectator ion, but the iron will react to form hexoaquo iron, and the hexoaquo iron acts as a weak acid as well. So writing hydrolysis reactions for the following hydrated cations, these are those ones where we get the hexoaquo. The water actually acts to make it acidic. So with this one, with the tin, you can see that when we mix it with the water, we're going to subtract 1 hydrogen ion from the original, getting the conjugate base there, and it's going to form an H3O+. We're getting that directly from that Bronsted-Lowry acid base chart. Same thing with the copper here. When we mix them with water, we're going to take 1 hydrogen ion away from that the copper solution there, and we're going to get a hydronium. Hexoaquo iron there. We're going to subtract 1 hydrogen ion from that, donate it to the water, and we get Fe, H2O, 5, OH, and 2+.